Our next presenter is Dr. Zining Wu. Dr. Wu serves as the Chief Technology Officer at Marvell Technology Group, a position that he's held since January of 2014. In this role, Dr. Wu is responsible for overseeing all technical aspects of the company, including establishing the company's technical vision and strategic innovation initiatives, and directing R&D project execution and future growth. Prior to his current position, Dr. Wu was Vice President of Data Storage Technology at Marvell. In this role, he led the engineering groups that delivered innovative technologies and products for the hard disk drive and solid-state drive controllers. Dr. Wu holds a Bachelor of Science degree in electronic engineering from Tsinghua University in Beijing, China, and a Master of Science degree and PhD in electrical engineering from Stanford University. Please welcome Dr. Wu.
Thank you. Hello, good morning, good afternoon, everyone. It's a real pleasure for me to be here for this keynote speech. As someone working in the data storage industry, I feel very lucky these days. We are clearly in the middle of a data explosion, right? So this is good news for those of us working on something related to data storage. Because as you can see, there's a prediction, as some of the previous presenters already talked about. The data that will be created, replicated, or consumed in a single year in 2020 is expected to be 44 zettabytes, right? So that's a large amount of data. Of course, not all of those data needs to be stored. So people will ask, like, why you talk about this large data here? Well, even though not all of them need to be stored, but there's also a large possibility that over the years, more and more data will be analyzed and tagged. That means they need to be able to go through the network, go through the creation, go to the CPU, and be analyzed, right? So in that process, it will touch the storage either temporarily or permanently. So with large amount of data, with a large percentage of the data being analyzed, that creates a large demand of storage. Of course, with that data analysis, it comes in two parts. One is the storage, the other one is computing. And ideally, we want the balance between these two, right? CPU, computing, and the storage needs to balance. But the problem is, over the past decade or past 3-4 decades, the CPU has always improved faster than data storage, right? So I just chart here from the year 2000 or so to today. CPU has been growing at a much faster pace than storage. And since year 2008, the good news is SSD came about and helped to close the gap. So it improved the throughput, the storage size throughput, by more than 10x. But even that, there's still a huge gap between CPU and storage. Another good news came in the last 1 or 2 years with a lot of new non-volatile storage technologies being announced. Those are the new storage class memories, such as MRAM, resistive RAM, 3D crosspoint, carbon nanotube, and so on and so forth, right? So it helped to create a storage layer that bridges the gap between the traditional hard drive or SSD and the CPU. With that, let's first take a look at where we are, right? How do we put all this storage together and compare their performance and cost? Right? First, if we normalize everything to the hard disk drive as the baseline, right? That's the 1x. Now we chart the performance versus cost for everything else. We can see on the far end, on the top right corner here, we have the SRAM that delivers the best cost at the highest cost as well, right? The best performance, best cost. The best performance, highest cost. Right? And HDD is the lowest one here, right? And there's a DRAM sitting in between, NAND flash sitting in between. And now it comes the new storage class memory type of NVMs, MRAM, resistive RAM, and 3D crosspoint, and so on. It's not performing quite as fast as DRAM yet, but it's also much cheaper than DRAM. So it sits nicely in between DRAM and NAND flash. Okay. So the nice thing about here, if we chart this performance over cost, it follows almost a straight line. Right? I call this a line of trade-off. So it's because of this line trade-off, all those different type of memory, different type of storage can coexist. Right? Otherwise, if you think about this, if something gets too much off the line, if there's one type of storage totally above the line, it should just dominate the market. Right? If one of the storage type is totally below the line, it shouldn't exist to start with. Right? So this is a line of trade-off. Along the line of trade-off, we can mix and match and supposedly a hybrid different type of storage media and create something with even better performance at a lower cost. Right? For example, people have done this, right? Put a hybrid of SSD and hard disk drive together. Right? By doing that, we can achieve a cost close to hard disk drive at a performance close to SSD. Right? So that one was already shown in some prototype. Now, the question is, can we achieve something even better with the new class storage class memory as the storage class memory type of NVM, right? So can we achieve something at a cost close to maybe to the NAND flash at a performance close to the DRAM, right? Well, the answer is yes, we can do that, but the design is very tricky. Okay, let's see why is that. First, let's review what we have done here, what the industry has done to bridge the gap between hard drive and SSD by doing a hybrid between these two media, SSD and HDD, right? So people put two layers of storage here, the first layer being SSD, and that potentially is a smaller SSD as a cache. And the second layer is a big, second tier is a big hard drive with a lot of capacity built into it. Right? So when CPU has a data read command, right, want to access some data, it first goes through an address lookup stage. You see if that address is in the SSD cache or not. Right? If it's in the cache, that's great. So we'll just get that data from SSD, right, and send it back to CPU. And if not, then another layer of lookup, address lookup, and address translation need to happen. Right? It need to locate the data in hard disk drive. Right? Now get that data from hard disk drive, send it back to CPU. And in this process, it also needs to find out whether it need to replace some of the old data in the SSD cache. Right? So this is a well-known cache data replacement problem. So with that, basically, there are two tiers of address lookup. Right? The first one is to look up whether it's already in SSD. The second tier translates another translation of a hard drive. And there's the data replacement cost associated with the second tier. So with that, let's take a look at the performance hit by doing this type of hybrid compared to just a one tier system. Here we use T1 as the time, the delay, the overhead for the first tier address lookup. And we use T2 to represent the second tier lookup. Okay? And here we assume there's a hard drive access time that's in the milliseconds, 10 milliseconds, SSD in 100 microseconds. Maybe this is a MLC or TLC type. With that, we can see that our average access time is a function of this T1 and T2, right? And plus a function of the hit rate, the cache hit rate, and SSD access time, and the cache miss rate, and HDD access time, right? And cache miss rate is just 1 minus hit rate, right? So with that kind of average access time, the cost in mind, let's see if we want to design a system that perform within 1 to 2% of the original SSD performance, right? What kind of design parameters we get and whether we can achieve it. So here, I give example of two different design targets. One is 1% access penalty there on the left, and the second one is 2% access penalty, right? That's the table on the right. Right? So here, we list this cache access or cache lookup delay, T1, T2. Right? And for different combination of T1, T2, we calculate the requirement on the cache miss rate. So the cache miss rate has to be lower than this whatever listed on the table to make the whole system feasible, or to another way to put it, to achieve the 1% or 2% design target. As we can see here, in the first case, 1% performance penalty, it put a pretty tough requirement on T1, T2, right? So if this cache lookup overhead is too much, right? T1, T2 become too high. No matter what you do, right? You cannot design a system because you need to require like a 0 cache miss, which is clearly not possible. As we get a better design on the cache engine, so if we can reduce the overhead of cache lookup, right? In that case, we can relax our requirement on the cache miss rate. So in this example here, circled in the black column here, if T1 can be below 0.1 microsecond, T2 can be below 10 microsecond, which both of them are achievable. The required miss rate is close to 0.01%, right? So that's doable. Right? And of course, if we can relax our requirement on the overall system performance, hybrid system performance, like the table on the right, then everything becomes much easier, right? The T1, T2 miss rate, there are a lot of combinations that can make it work. So clearly, there's a trilemma between the performance target, right? Between the cache overhead, T1, T2, and the miss rate requirement, right? These three variables need to be balanced in a design, in a system design. Right? So from this example, we see that the first tier lookup time, T1, needs to be much shorter than SSD access time. Right, so for that, like 0.1, like the black column circle there, 0.1 microsecond, that requires hardware-based design to do that. Right? And the second tier overhead, T2, need to be far less than the hard disk drive access time. And we give you example here in the tenths of microsecond. For that, 10 microsecond, that can be achieved with software. And that's actually what people do these days. Right? So T1, T2, basically here what we are showing, it kind of intuitively makes sense that it needs to be, each tier's cache overhead needs to be much less than the access time, right? The cache access time. Okay. Another requirement, if we look at the miss rate, cache miss rate is, for this type of system, we need a very high hit rate or a very low miss rate. Right? This is due to the large performance gap between the SSD and the hard disk drive, because we don't want to access hard disk drive. Right? We try to avoid that. We try to avoid that the most. Try not to access it as much as possible. Right? So whenever you have a large gap between two tiers, that make the design even more difficult when you hybrid them. So to achieve a very high hit rate, right, what we need to do is to have a very large cache and very high associativity. High associativity means you should be able to place the data, the cache line, anywhere in the cache. That kind of freedom helps you to lower the miss rate. Right? And that's actually exactly what the people are doing with the current computer memory hierarchy. If you look at the typical computer today, it has all the way from L1 cache to hard disk drive with several layers of cache. It basically follows the two principles I just talked about in the previous slide. The first one being that from each tier, like high tier to lower tier, right? Each tier going down there, it needs to achieve a lower and lower miss rate. That means the high rate needs to get higher and higher. That means you need to have larger and larger number of entries when you go from one tier to the next. And you need to have higher and higher associativity when you go from one tier to the next, right? So here on the right side, you can see a comparison of a cache miss rate with different size of cache and different type of associativity. So basically, it confirms that the larger the cache size and the higher the associativity, the lower the miss rate, right? So you can see that basically our current memory hierarchy is following this trend here. And the second principle, we said, okay, we have to have the cache overhead much smaller than the cache access time itself. So that dictates for the higher tiers, like L1, L2, the cache lookup engine has to be implemented in the hardware, pure hardware and simple hardware, right? While for the lower tiers, like the DRAM and HDD tiers, things can be handled in software. Right? So in this typical memory hierarchy today, the higher tiers focused on performance to achieve the best performance. The lower tiers is focused on the highest possible hit rate and the cost, because we don't want to use them. So we want the hit rate to be as high as possible. So now let's see how we apply the same principle and same tiering idea to the new storage class memory, right? We call it a new NVM here. Here, I'm using the similar setup, try to make a two-tier storage by combining DRAM here with NVM, right? So DRAM will be the first tier, NVM will be the second tier. And the NVM can be either SCM type of NVM, the new ones, right, as MRAM, RAM, or it can be just a plain NAND, right, the NAND flash. Let's see how it goes, right? So this time, we give our design target to be within 0.1% of the DRAM access time. Why is that? Because now we are comparing the overall hybrid system to the DRAM, and DRAM is performance critical. So we can only take a very, very minimum penalty. So with that performance requirement, 0.1% penalty, and let's assume some cache miss rate about 0.005%. That's the first column, right? Then it turns out that if we use the new NVM, right, SCM type of NVM, because that access time is quite fast compared to NAND, we can achieve such design. We can achieve this design target of within 0.1% of penalty. Okay? But the requirement is the cache lookup overhead needs to be within 0.2 microsecond or 200 nanosecond. Right? That's quite stringent. And if we try to use NAND as the second tier, it turns out no matter how you do it, it's just not achievable because NAND is too slow for this. Right? A similar thing, if we drop our, if we can further decrease our cache miss rate, right? Instead of 0.005%, we can get to 0.005, like 4.05%. We can actually relax the rest of the design parameter, right? So even regular NAND can do it. But to achieve the 0.005%, that's possible, that's doable. To achieve the last one here, it's almost impossible, right? In terms of cache miss rate. So that basically says, another way to look at this is that when we have those faster memory for us to tier, right? For us to put in the memory tier, we need cache engine that goes consider the characteristic and access time of that layer, that tier of memory. Okay. So here, for example, I listed a relative time, right, of the cache access time, the NVM access time versus the cache engine, right, overhead. We can see that if we stay with the old time with NAND, right, because NAND access time is relatively slow to the new NVMs, so even if we do a software-based cache engine, it's okay, right? The overhead is only like 2 to 3%, negligible, right? But now if we change to the new type of storage class memory type of NVM, like RAM, MRAM, now if we use the same software-based cache engine, it will dominate performance, right? The software engine starts to dominate performance, and the whole overall system is going to take a big penalty. So in that case, we need to go to the rightmost column there, in the sense that we need to develop another hardware-based cache engine for the new NVMs. Okay. So with the new NVM, with the introduction to hardware-based cache engine, that can create another tier in the memory storage hierarchy here. So we put SCM type of NVM right between SSD and DRAM. Right? By doing so, our goal is to lower the requirement on DRAM. So instead of doing millions of entries in DRAM, we can reduce it potentially to hundreds of thousands of entries. So we can reduce the DRAM size and still keep the same performance. But that requires, remember the T1, T2 argument, that requires a very fast design of the cache lookup engine. Or another way is to minimize the overhead of cache lookup, both in the DRAM and the SCM NVM tier. So people may say, hey, it's no big deal, right? People know how to deal with that because in the past, the page table is like that. Page table is millions of entries, and we do lookup and so on. But here, it's this new cache engine is going to be much more difficult than the page table lookup, because on one side, it requires very high hit rate. So it requires millions of entries. We need to be able to go through millions of entries. On the other side, it requires very low overhead. We're talking about nanosecond, right? Not millisecond. Not millisecond that can be handled by software. It's nanosecond. So with these two extremes, right, extremely high hit rate, extremely lower overhead, right, it makes the design very, very difficult, very challenging, and contradicting each other. Because on one side, large cache side, fully associative cache will be the best for hit rate. But in the same time, if you talk about large cache size, fully associative is terrible for the overhead. Okay, so how do we solve this problem? Well, luckily, we did figure out a hardware design. Right? We call it a final level cache. It's a cache engine, or FLC. It can achieve both the low miss rate and low overhead, and extremely low miss rate and extremely low overhead. So how do we achieve both? Well, for the low miss rate, we support very large cache. We support millions of entries with a very fast lookup. So we support the cache entry in the size of gigabytes, right? Multiple gigabytes. And we also support large cache lines, right? 16 kilobyte or larger cache line. And we support fully set associative cache, so you can place data anywhere. In the meantime, we try to reduce the overhead by doing a pseudo CAM-based design to do full automated hardware-based lookup. And we do hardware-based replacement policy, pseudo IRU replacement policy for that. So overall, we can achieve the overhead of less than 10 clock cycles, right, for this large type of millions of entries of a cache lookup engine. Right? So with that, if we have a gigahertz clock, we can control the overhead to within the 10 nanosecond. So we put our FLC to test. Right? We don't have NVM, the new class, storage class NVM. So we did that with a hybrid drive, SSD hard drive hybrid. We can see that when we put our FLC engine together with the hard disk drive, it performs very close to the SSD. That's the one on the right. So in terms of if you look at the red bar, that's the PC Mark overall score. It's basically the same as SSD, right? And if we look at the bandwidth, it's also in the same ballpark. Right? So with FLC engine, we can essentially close the gap between two tiers of storage, or storage or memory. Okay. So that successfully addressed the performance issue, right? FLC engine, fast, can look up large cache, can bridge the gap between the new NVM and DRAM. That's great. We can put the new NVM into the storage hierarchy, right? But in the meantime, we need to also worry about cost, the cost of the lower tiers, right? Because even though the lower tiers, SSD and HDD is relatively cheap compared to the top tiers, still, The lower tiers, because we need so much of it, we need such a high, big capacity, the cost adds up, right? But good thing is I work in both hard drive and flash in the past. Both industry has did a lot of good work to bring down the cost, right? We just heard about the 3D NAND, and we still have the model here. So with 3D NAND in the next couple of years, we do expect the cost of lower tiers to continue to drop. But another component of the cost is not just the material, not just the media, right? It's also the controller cost. And Marvell is a controller company. So I'm going to spend some time to address the controller cost here. Controller is basically SoC, right? And if we look at the SoC, a chip, right? What's the chip cost? Well, if it has some fixed cost, that's the R&D cost, the mask cost, and packaging and RE. And that fixed cost got amortized over the chips that's sold for that design. The second component of the cost is the variable cost. That's per die cost, right? Well, in the past, the fixed cost part, right, once it's amortized, it becomes a very small portion of the overall cost. That's the good news for the SoC industry. But going forward, right, people are predicting the cost of designing or manufacturing an SoC is skyrocketing. Right? So people are talking about $300 million to develop a new generation of SoC in the 14 or 16 nanometer process. Of course, we can argue not all the new SoCs need a completely new design. So not every SoC will cost that much. But nevertheless, even we put a modest estimate, just say $100 million to develop SoC, that cost is still a big adder in terms of the unit cost. So we can see that in this equation here, all the top three numerators are increasing, right? The R&D cost, mask cost, packaging, RE increasing. Number of chips could potentially decrease because the market got more and more segmented, right? If you want to use one design for one segment, you cannot sell too much, right? So then the number of chips decrease. So the amortized fixed costs become a bigger portion of the overall unit cost. To see how bad things are, let's just assume a modest design, right? A $40 million R&D cost design for an SoC, plus a $7.5 million NRE. That's the masking NRE and packaging NRE. With that, and let's assume like you have certain volume and see how much we can amortize over the volume. Right? We see that even setting this design at 10 million units, which is not small, we still bear almost $5 of amortized cost for this. Right? So clearly going to the advanced CMOS technology, the amortized cost or amortized fixed cost is a big concern. Well, we can potentially solve this problem by an idea that we have been developing at Marvell. We call it modular chips, or MOCHI, right? The idea goes like this. Instead of, for example, we want to address two SATA market, one mid-capacity, one high capacity, right? So instead of do one design for each, which at the end probably costs about $50 million R&D cost for the first chip, and since the second chip is a derivative, it's similar, so it costs less. Let's just assume it's 20 million. So overall 70 million development cost. Then we address this both market, right, with two chips. Instead of doing that, with our modular chip design, we can do one chip and add a high-speed interface to that chip. Right? By doing so, we can use one design to address both markets. When we need to address the higher capacity market, we just connect two of them together through this, we call it modular chip interconnect or MOCHI interconnect. Right? So when we package two controllers together, we can drive a bigger capacity. Right? If we just need to deal with a smaller capacity, we just use one of them. So by doing so, we don't need to develop two chips. We save $20 million development cost. So apparently, the most important thing in this design is the interconnect layer. It's the MCI, right? MOCHI interconnect. It needs to be transparent. It needs to be low power and very high speed. Unfortunately, we have all this in our design already. Well, what we did is we have a design of this MCI, and we put it in test in a full SoC. Right? So we test, in this case, the upper link, we test the SATA speed with the native SATA connection. And the lower link, we test the SATA speed going through this Mochi interconnect, right? MCI interconnect. And to connect to that Mochi, we need a bridge, right? To bridge between the Mochi and the SATA. The good thing is, from our testing result in the lab, there's really no performance difference between the native case and the Mochi case. So we do have a solution for interconnecting chips to make it better. So to summarize, right, let's go back to our problems again. First of all, where we started, right? Well, we know there's a data explosion. And with data explosion, with more analytics being done, right, cloud computing and everything, it's all about data access. Right? It's all about getting data when needed and getting them at the right cost. Right? And we see that to achieve that, multi-tiered storage system is still essential in today's world, and probably even more so in with the new SCM type of NVM. Okay. And we introduced, we talk about how tricky it is to design a good cache engine for the NVM tiers, and we introduced a good design that can achieve a nanosecond of delay with millions of entries. And we introduced expandable controllers through our Mochi interconnect. That concludes my talk. Thank you.